Hello, I am Jung Han, and I will be giving this presentation. I will be explaining set 1, which cover LDA and QDA. Let's begin. This is the table of contents. We will explain LDA and QDA, discuss the trade-offs they entail, and then solve a problem using this concept. First, let's briefly discuss why we might use a Bayes classifier instead of logistic regression. In the previous section, we learned about logistic regression. Simply put, logistic regression uses the logistic function to estimate probabilities for two response class. However, we need a different approach for the following three reasons. First, when there is clear separation between class, logistic regression can become unstable. This is due to maximum likelihood estimation method. Second, when the predictor has a distribution close to normal distribution and the sample size is small, the new method may be more accurate. Third, the Bayes classifier naturally extends to problem with more than two classes. We will cover this in more detail in the later part. Due to these various reasons, we must consider a new model. Before explaining Bayes' theorem, let's briefly define the terms. Pi k, the probability that an observation belongs to the case class. Fk of x is density function, estimates the density of the predictor x value, x within the case class. Pk of x, posterior probability, the probability that an observation belongs to the case class, given that the predictor x has the value x. We can approximate the posterior probability by substituting the prior probability and the density function into the equation for the posterior probability. Therefore, the Bayes classifier uses Bayes' theorem to indirectly calculate the posterior probability, unlike logistic regression. And then classify the observation into the class with the largest posterior probability. The challenge is that the prior probability is easy to find, but density function is difficult to estimate. We need an estimate of the density function to estimate the pk of x. We use three methods to estimate the density function: LDA, QDA, and naive-Bayes. Since we will not be using naive-Bayes to solve the problem in set 1, we will omit it. Let's first look at LDA. LDA makes three main assumptions. The density function has Gaussian distribution. Second, the data in each class has a unique mean, mu k. The k classes share a common variance. This third assumption means that the data for all class share the same shape and orientation. The term linear is attached because this assumption leads to the effect of the predictor on the class being linear. Now we have the formula for the estimated density function. Here, uk is the meaning of the case class, and sigma k of k scale is the variance for the k class. And recall the third LDA assumption. We will assume that all k variants are equal. We will substitute this density estimate into the posterior probability equation. This gives us a new posterior probability equation. By taking the logarithm and removing the constant terms from this new equation, we can obtain the discriminant function. Assigning an observation to the class for which this discriminant function value is largest is ultimately the same as the result of the base classifier. Here we must focus on the area where the two classes overlap. We can define this boundary. To add understanding, let's take an example where k is 2 and pi 1 and pi 2 are equal. If set delta 1 of x equal delta 2 of x, we can derive the decision boundary equation. This equation is called the base decision boundary. One might wonder, since the discriminant function came from the estimated density function, why is this called the base decision boundary and not the LD decision boundary? The answer line is the question, do we know the true parameters? We assume the distribution is Gaussian for LD. However, we do not know the true value of the parameter that define the distribution mu k, pi k, and sigma scale. The decision boundary defined by this, the true parameter value is ideal optimal boundary. That is why we call it the base decision boundary. Since we do not know the true parameters, we must find the estimate for pi k, mu k, and sigma scale. These are equations for estimating the parameters. The pi k is usually known and can be used directly. If it is unknown, it can be estimated by LDA. Substituting this estimate into the discriminant equation and deriving the decision boundary through the same process as before gives us the LDA decision boundary. Let's assume this condition. The left side of the figure display two one-dimensional normal density function. The dashed line is the base decision boundary. The class of observation become the uncertain in the region where the two dimensions overlap. In case if pi1 and pi2 is 1/2, and we use this equation. And if x greater than 0, we classify 1. And if x less than 0, we classify 2. And the right side show a histogram of the 20 observations drawn from each of two classes. The dashed line is the basic decision boundary, and the solid line is the LDA. The figure show LDA approximates the base. Now, let's consider the case with multiple predictor. The multivariate Gaussian density function is showing the following equation. The key point here is that when P is 1, sigma scale is replaced by P by P covariance matrix. By substituting this equation into the base theorem equation, we obtain this discriminant function. The base decision boundary for two classes K and L is given by the following equation. Expanding the equation show that it is a linear expression in terms of x. The figure shows that the decision boundary is linear. Therefore, the base decision boundaries exist. We divided the predictor space into the three regions. In this P greater than 1 case, just like P is 1 case, we must estimate the unknown parameter, pi k, mu k, sigma. The process is identical to the piece one case, so the equation will be omitted. LDA estimate parameters substitutes them into the discriminant function and assign each observation to the class with the large value. Unlikely LDA, QDA assume that each class has its own covariance matrix. Under this assumption, the base classifier assigned an observation to the class for which delta k of x is largest. This is discriminant function equation. The QDA substitutes the estimates for sigma k, mu k, and phi k into this discriminant function and likewise classifies the observation to the class with the largest value. Since the discriminant function is quadratic of x, why is the assumption the k class have a common covariance matrix important? In otherwise, why would LDA be prepared over QDA or vice versa? The answer lie in the bias-variance trade-off. With p-predictor, estimating the covariance matrix requires estimating p times p plus 1 over 2 parameter. QDA, since QDA estimate a difference covariance matrix for each class, it requires estimating k times. So this becomes a best number of the parameters. But conversely, LDA assume a common variance requires the estimation of only k times p linear coefficient. LDA exhibits lower flexibility and lower variance, but high bias. But QDA is high flexibility and high variance, but low bias. LDA is favorable when the number of training observation is small and reducing variance is critical. QDA is favorable when the training set is very large or when the assumption of common variance across the K class cannot be maintained. We can now solve the following problems using this concept. Problem A. Question is, if the base decision boundary is linear, which models will exhibit better performance on the training set, the test set? When training set, QDA is more flexible than the linear LDA. QDA will better optimize for the training data, modeling more of the noise on outlier, and thus achieve a lower training error rate. When test data, LDA will show better performance than QDA. Since the true base decision boundary is linear, using the low variance LDA model will yield more stable prediction with less overfitting. Question B is, if the base decision boundary is non-linear, which model will be more advantageous? When training set, QDA perform much better. QDA allows for difference covariance metrics per class, enabling it to run the non-linear boundary. In contrast, LDA is being restricted to a linear boundary will result in high bias. When test set, since the base decision boundary is non-linear, QDA still tends to the better. However, if the sample size is small, QDA's higher complexity can lead to overfitting, resulting in higher test error than LDA. Problem C is as the sample size and increase, will QDA's test prediction accuracy improve, decrease, or remain unchanged compared to LDA? If the actual base decision is the linear, as the sample size increase, the LDA's assumption align with the true distribution and its bias approach zero. QDA has more parameters to estimate because one covariance matrix per class. So with small sample, its variance is large, leading overfitting. If the actual base the non-linear, base boundary non-linear, QDA's performance improves as the sample size increase. LDH cannot approximate the non-linear boundary well, so its bias will steady increase. So QDS will decrease relative to LDA. The next problem D is determine if the following statement is true or false. Even if the base decision boundary for a given problem is linear, QDA is flexible enough to represent a linear decision boundary, and therefore it will achieve a lower test error rate than LDA. Answer: this statement is false. This issue was sufficiently explained in problem C. While QDA is flexible enough to express a linear decision boundary, it has a lot of unnecessary degree of the freedom, which increase the risk of overfitting and leads to higher variance. Therefore, when the actual base is linear, LDA generate yield of a lower test error rate because its constrained model has lower variance. Okay, this concludes my lecture. Thank you for listening.